Scaling. This is the first linear transformation that we learned in this material. So what does it do? Basically, if we have this geometry, well, it's a square right now, then we're able to stretch or shrink it. So if we want to make it larger in x-axis or maybe shorter in y, then this is what scaling does. It scales one of the axes, or well, both of the axes by the given amount. So this is an example from Scikit-learn, and well, up here you can even see a matrix. So this is like a 4x4 matrix. We will learn later on why is it so big, but basically you can see that when we change, let's say, the x factor, then this value here on the diagonal also changes. And what's happening here is that the vertices of this geometry or this parallelogram here will get scaled based on the factor that is in the matrix. A simple version of that is just a 2x2 matrix for 2D scaling and a 3x3 matrix for 3D scaling. So it kind of stretches or shrinks the space, and there are these scale factors on the diagonals, and everything else in the matrix needs to be 0. For example, here the Sx is the scale factor for the x-axis, and Sy is the scale factor for the y-axis. So this is very similar to the example we had in the previous video, where we just wanted to multiply one of the coordinates by 2, and it was on the diagonal we had 1 and 2. So this is a scale matrix. If on the diagonal that would be 1 and 2, so we keep the x-axis the same and we scale the y-axis by 2. Now there is this one interesting thing about transformations. It's that we can see what they do by seeing what they do to the standard basis. So for example, here we have this standard basis, we have one point, and if we multiply this point with a matrix, and for example here it just scales the x-axis 2 times, so 1.5 results in 3 for the transformed point. And compared to this, another way of understanding is if we see what it does to the basis vectors. So before we have this basis vector e0 and e1, and we could actually apply the matrix on those and see what happens. So e1 stays the same, but this e0 becomes 2 times larger. So looking back, this coordinate system here has this basis vector, but if we multiply this basis vector with our matrix, then it becomes 2 times larger. But if we do that, we get think of this space as being defined by now these 2 transformed basis vectors. And if we think about it like that, then the coordinates of this point will stay the same in this transformed space. So we could say that these transformed basis vectors, well, these are these ones. And where does this lead to? So if we transform the basis vectors, then there is this trick that we can actually read the transformed standard basis from the columns of the transformation matrix. So over here, we have set the coordinate system to be defined by the standard basis again. So these units are the same units that are over here. But if we look at the transformed basis vector, then its coordinates are now 2, 1. And well, the other one has 0, 1 as coordinates. Now if we try to come up with a matrix that does this transformation, then the columns of that matrix will be the transformed basis vectors. So the first column here will be the transformed first basis vector. And the second column here will be the transformed second basis vector. So if you put the coordinates in, then the matrix that does this transformation that we just saw is 2, 0, 0, 1, where the first column is 2, 0, the coordinates of the transformed first basis vector, and the second column is 0, 1, the coordinates of the second basis vector. And now that you learned about scaling, you know that when on the diagonal we have 2, 1 and everything else is 0, and this is scaling the x-axis 2 times, which is exactly what we saw here. Now if you look at the preliminary math tasks handout that you might have got, then task number 16 implies this result. So it asks you to put the basis vectors into a transformation, matrix vector multiplication, and see what the result is. And the result will be just the column of that transformation matrix. Now from this video, you should understand the scale transformation. So it kind of stretches or shrinks the space. Its matrix will in 3D, it's similar in 2D. On the diagonal, we have scale factors and everything else needs to be 0. And you should now also have a better understanding of the linear transformation matrix. The columns of such matrices are the transformed standard basis.